as you've got a circuit that is a resistor and a capacitor in series. Resistor's 4 ohms and the capacitor is 120 microfarads. Yeah?
Yeah.
And that's got a voltage connected to an AC voltage of this, what's in the question, which is 560
sine
150 pi t plus 220 sine 450 pi t. So these two, you've got two sine waves added together. Yeah.
Yeah.
And this is what's called the fundamental, because that's the lowest frequency, or F1. And this is, because this is 3 times, so 150, this is the third harmonic. Yeah?
Yeah.
It's got 3 times the frequency. Omega is 3 times as big. Both those are in, both of those voltages are in V is equal to the amplitude times sine omega t plus or minus alpha form. But there is no phase angle in either of them. But that's the form they're in. Yeah.
Yeah.
So you know that this number here, 150, is the omega for the fundamental. It's omega 1.
Mm-hmm.
And this one is omega 3. Yeah.
Yeah.
So the first A says calculate the fundamental and third harmonic frequencies in Hertz. So you've got them in fundamental omega 1 is equal to 150 pi. Yep.
Yeah. Fundamental omega 1.
But we also know that omega 1 is equal to 2 pi times F1 in Hertz. Yeah. Therefore, we can rearrange that to say F1 is omega 1 over 2 pi. So that's 150 pi over 2 pi equals 75 Hertz. Equally, you should be able to do the other one. So you've got omega 3.
So 100, do you say it's at 150 pi over 2x, is it?
Yeah, it's 150 pi over 2.
Pi,
So you
so
rearrange this formula, yeah?
Yeah.
So rearrange this formula so that you can find F.
Yeah.
All right? So now you can do the same for the third harmonic, which is this part of the waveform here.
So y omega 3 equals 220 pi.
That's 450 pi, look.
Oh yeah, yeah.
Yeah, 3 times the fundamental.
450 pi.
Divided by 2 pi.
Yeah.
You should get 225.
Yeah.
Yeah? Okay.
Yeah.
So that's just getting the frequency in Hertz when you've been given the frequency in as omega, as radians per second. Yeah?
Right. Yeah.
So that's 2 pi. You should have 2 pi f3. So f3 is omega 3 over 2 pi.
Yeah.
And you've done 450 pi over 2 pi equals 225 hertz.
Yeah.
Yeah. Okay.
Yeah.
Easy.
So the next part of the question says, using suitable calculations, show that the impedance of the circuit at the fundamental frequency is 18.13 ohms, angle minus 1.35 radians. So this is where, as an example in a question of where you know what the answer is, but you just got to prove it. So you've got to know what to do to prove that. Yeah. So how can I calculate the impedance of this circuit, Z total?
That was what I now add up. Hang on.
What would be ZT equals. Hold on, I've got the handout here, so anything in here.
Come on, come on. Where are
Just
you?
going to take the diagram across on the other page.
Come on.
Is that would it be ZT equals VT over I? T? No?
Yeah, but you know V, but you don't know I.
So we've got to work out I, have we?
Yeah, but
Right. It's
you've got a resistor and a capacitor in series. Go on, Callum.
C1 equals 1 over omega C. Omega C.
So in its simpler form for a minute, that's going to be R plus XC, and then we need the complex form, so we need to include, and that's not plus, that's minus for a capacitor. Yeah.
Minus.
Mm-hmm.
All right. So you've got a capacitor that's going to be R minus XCJ, because you get a negative XC from a capacitor. Yeah. So we need to, as Callum was then saying, you then got to say you need to calculate XC, Callum, don't you?
Yeah. So
is that what you were saying?
Yeah. So that equals ZT. That equation we now said. So XC is equal to 1 over omega C. Is that correct?
Yeah. And we're looking for, what you need to be careful here is we're looking for XC at the fundamentals. So we need to make sure we're clear that we're talking about XC1 at the fundamental frequency is equal to 1 over omega 1 times C. Yeah, because we got two frequencies in this question, remember? We got omega 1 is equal to 150 pi, and we got omega 3 is equal to 450 pi. So we must use the right one. So that's 1 over 150 pi times 120 times 10 to the minus 6, sorry, 10 to the minus 6 equals.
Right, I have to change this thing in a pissing radian now.
Yeah, needs to be in that.
Ratio, what are you doing? Set up. Yes, there you go. Systems tech.
17.68.
I'll take that. Units, Dan?
Ohms.
Yeah. Okay. Therefore, the total impedance is 4 minus 17.68 J ohms. And then we can convert that to polar. If you do that, you should get the answer that was in the question. Calculator in radians, remember?
Oh, shove your syntax error up your jacksie.
We are recording, Callum.
18.1 to 13.
18.13 ohms angle.
Minus 1.35 radians.
Yep. Which is what you got in the question. Or it might be 1.34. I don't know. That's what I got written down here, but that's near enough. Yep.
Well, how did you get that again? Because I keep getting syntax.
Do the so on your calculator to do that conversion, Callum, you need to push shift.
Yeah.
And then on the plus button, the shift function is polar, POL.
Yeah.
Yeah. And then you press, there you get a set of open brackets. You put in 4. Yeah. Then you shift again. And on your close brackets button, you've got a comma.
Ah.
So you do that. Yeah. And then you put in minus 17.68. Close the brackets. Press equals.
Oh, yes. There you go.
And you get an R value of 18.13.
Yeah.
And an angle. Oh, mine is in my calculator's in degrees, but you get the angle as well, yeah.
1.35. Yeah, wonderful.
Minus 1.35.
Minus. Oh my God.
Yeah.
Yeah.
Okay. Yeah. So that's that then. So that's your. If you want to go the other way, you start off with shift and the minus key to go to the rectangular. Yeah.
Rectangular, and the same thing. Just put a comma in the middle.
Yeah, you would do if you can go backwards and forwards to your heart's content. All right.
Yeah.
Okay. Right. I'm going to move on to part C now. Then, yeah.
Yep.
So part C says find the current due to the fundamental, doesn't it? So up to now, if you get all that right, you'll have earned 6 marks. Yeah. So show using suitable calculations that the current due to fundamental is 30.89 sine 150 pi t plus 1.35 amps. Yeah. So how are we going to do that? We're looking for finding I1, the fundamental current. Yeah. How can we do that?
V over ZT.
Yeah. So, but we must be specific. That is the fundamental voltage over the impedance at the fundamental Z1. Yeah.
Right.
I believe that's 560 volts.
Oh, Peter's
angle,
Hi, mate.
0 degrees. Peter.
Good morning, all.
Yeah.
Morning.
Fuck time,
Good to
guys.
see
I kept quiet because I didn't want to interrupt. So, because obviously you were mid explaining. So.
You're following us, though, yeah.
Yeah, I joined at the beginning of part B, so that's fine. I'll go back and find A later.
Yeah, that's no problem. Good to see you.
Yeah, so I was watching the old SAS thing on the telly and I lost track of time. Sorry.
560 angle 0 over our 18.13 angle minus 1.34 already calculated. Yeah?
Yeah.
So you've got to do that polar division. You remember how to do that?
Yeah, 560 divided by 18.13.
Yeah.
30.89.
Yeah. That's amps. And then the angle
is
you're doing 0 minus 1.34.
So plus 1.34.
Yeah. Yeah.
Yeah.
So this is the amplitude, and this is the angle, phase angle of the current. Yeah. So therefore, I1 must be 30.89 sine, and then the omega was 150 pi times t. Yeah, and then it's plus 1.34 radians of phase shift. And that's, you've then proven the answer given, and that's amperes.
Mm-hmm.
All right.
Yeah.
Right.
So that's part C of this question. Okay.
Yeah.
So what does part D say?
It says
Calculate the third harmonic current and write a complete expression for the total current flowing.
oh my god.
Yep. So what do you think we need to do?
Well, we just do exactly the same as we just did for that one, and then add them
You
together.
see the hand holding of giving you the answer you're heading for has gone away now. Yeah.
Yeah.
So you're on your own in that sense. Yeah.
Right.
All right. So what are we going to do then?
So we will do V over ZT, but that'll be that one. This the next one along 220 sine 450 pi.
You're gonna go the I3 is the amplitude of the third harmonic volt sine wave over the impedance of the circuit at the third harmonic, which is not going to be the same as it is at the fundamental, because the impedance of the capacitor changes when you change frequency, remember.
Ah, but we worked that out at the start, didn't we, as well? We got that at the start.
You worked out XC at the fundamental, but not at the third harmonic. So we need again to recalculate Z3. It's going to be R minus XC3. Different frequency, different XC value. Yeah, R will stay the same because there's a linear component, but XC will change. So what you've got to do now is go and calculate the new XC. Yeah. Turn that into a new total impedance in polar form. And then you can divide that into the voltage to find the third harmonic current. Yeah. Which then you can write a whole expression for all the current with respect to T. So have a go at finishing that off now, because it's not that different to the last one. Just got to bring it all together at the end. All right. I'll pause the recording for a bit, have a go at doing part D, and then we'll come back to it. I'll just go through that again. So what we've done for the third harmonic current, as said, it's equal to the third harmonic voltage divided by the third harmonic impedance. We've had to calculate the reactance of the capacitor at the third harmonic, 5.895 ohms, to calculate a new total impedance in polar form of 7.124. Then we can use Ohm's law to calculate the third harmonic current, and then add that onto the fundamental current to get an expression for the whole thing. Yeah, so that's part D. We're happy with that?
Mm-hmm.
Yeah.
Yeah. Right. Next bit is, so part E is probably looking at resonance. Yeah. Show that resonance with a third harmonic will occur if an inductor of 4.17 millihenries is connected in series with the capacitor and the resistor. This question tests you know what's meant by resonance. So regardless of whether you can do a whole load of calculations, do you know what it means by resonance? How can you prove that adding a 4.17 millihenry inductor into that circuit will mean that you have a resonance situation? Anyone remember? It is a good while ago, so, you know, unless you're doing this kind of thing every day. At resonant frequency, FR, right, we'll call it, XL is equal to XC. Yeah, and a saying, prove or show that resonance would occur if we put a 4.17 millihenry inductor in that circuit. We're going to prove that resonance happens with a third harmonic frequency. So we know that we're looking at omega 3 is equal to 450 pi. Yeah. From part, and that's XL3 and XC3, from part D, XC3 equals, and what was it? 5 point something ohms, wasn't it? 7 point something ohms. $5.895. How can we calculate XL3?
Right, well, XC3 equals 1 over omega 3 C.
C, yeah. We calculated that in the last part, Callum. That's 5.895. But how do we calculate XL? What's the formula for XL?
What is it? Oh, it's 2 pi FL.
Yeah, or omega, because omega is 2 pi F, yeah? So it's omega 3 times L. So it's 450 pi times 4.17 times 10 to the minus 3. You should get 5.895. You should get.
Yeah.
Yeah. To the same number of significant figures. Therefore, resonance will occur at third harmonic. Yeah, but that getting those 4 marks depends on you remembering and understanding what resonance means. Yeah. As well as being able to do the calculations.
What does resonance mean?
It's that point, Callum, where those two, remember XL and XC work opposite each other because they got completely opposite angles.
Yeah.
So remember your full impedance formula for a series RLC circuit is R plus XL minus XC J. Yep. So at resonance, if these two numbers are the same, XL and XC, 10 and 10, the result of that is 0, isn't it?
Yeah.
If they're both equal, therefore, at resonance, your ZT is equal to R, just the resistance.
Oh, right. Okay. That's what you were saying. That's bad, isn't it? Because that means that you get like massive...
Yeah, because as low the impedance at resonance, series resonance, is as low as it can be at any frequency.
Yeah.
And so you're going to get a much higher current flow because your inductor and capacitor aren't contributing anything to the impedance.
Yeah. Yeah, I see what you're saying.
All right. Yeah. Which is the flavour of the next part of the question. All right, because F says, I'll find it here. Using super calculations, determine the third harmonic current at resonance and use it to determine the voltage across the capacitor and the inductor. Yeah. So what you've got to do now is F at resonance, ZT is equal to R plus XL minus XC J ohms. But as XL equals XC, Z3 is equal to R only, which is equal 4 ohms.
Oh, that.
Yeah.
Mm-hmm.
So I at resonance is equal to the voltage at third harmonic divided by the resistance, which is equal to 55 amps. That's just the contribution from the third harmonic current. Yeah. So original 30 odd from the fundamental is still apparent as well. Okay.
Yeah.
And from that, we can calculate VC is equal to I resonance times the XC, which is 55 times sorry, yeah, I've got an XL, which is 55 times 5.895, 324 0.2 volts. Yep. Okay. In other examples, that could be very, very much higher than that, all dependent on the resistance. If you only had a resistance of an ohm, we'd be talking about hundreds of 220 amps flowing at resonance. That's why you got to be careful, because this can turn into thousands of volts quite easily. Yeah. Okay. And VC is going to be the same, because this value is exactly the same. It's just that one would have a positive 90-degree angle and the other one would have a negative 90-degree angle. So they're completely out of phase with each other, but they can be very large. All right.
Good.
Now, there's a little bit of a tag on the end of the question as presented, and that is that in the actual exam, for the last part of the actual exam, be a further 3 marks for you to understand the effects of the calculated harmonic current and voltage on the components of the circuit. So if you think we got a voltage of 324 volts here across the capacitor, if that's only designed for 200, that's going to go to 220. Yeah. Also, is the conductors of the inductor able to take 55 amps without burning out? They're the kinds of things that you need to realise. So if this third harmonic was an unwanted harmonic, i.e. that was interference with what you wanted the fundamental to be, then you could have problems. All right? So that the last part of the question may well test that understanding. All right?
Yeah.
So your second question, which you probably won't get time to have a full go at today, you may well remember doing this, is using the Fourier series to find a Fourier series for a square wave. And I bet you don't remember doing that.
No.
No. You have to use the 3 formulas given. So IO is equal to this. Hang on, let's just get the that's the problem 2 in your handout is completely different to what I've got in my solutions.
I've got
no, I'm going to be honest with you. You ain't getting a Fourier series question in your exam.
What?
You hang on.
Yeah, on that sheet you give us the Fourier series.